Hello everybody. In this video we're going to start talking about the periodic table and the periodicity of elements. So from what we learned before in the previous videos, we know that there are kind of same pattern of filling the electrons in different energy levels, and from this we can find similar properties of elements, and that's why people were interested in finding how the elements are arranged. And in this video, we'll see first what are the order. In this chapter, we will pass by the attempts that were made to develop the periodic table. And some of you might not know that the periodic table that we know today which is the modern periodic table by Demetri Mendeleev, is not the only periodic table that was developed. There were early attempts that were not as successful as Mendeleev's periodic table. And then we will talk about the periodicity of elements, which means that how the properties of elements are related to its position in the periodic table, and how we can predict the properties of elements and know how they change as we go right or left or down or up. And we will talk also about the shape of the periodic table and how the electronic structure affects the shape of the periodic table, which is pretty interesting actually. So the first attempt that was made by the French geologists Alexandre de Chamcourtois. I think I pronounced it right. And his periodic table was very interesting actually. He made the periodic table as a cylinder, so it wasn't put on a piece of paper as we all are used to now. So he put the elements with the increasing of the molecular weight. And if you remember, we mentioned before that the molecular weight was, or the atomic weight was, the criteria of differentiating between elements, and that's why the periodic, or the early attempts to make periodic table, were all based on the atomic weights, not the atomic numbers. So what he did is, as you see here, that this might be more clear, that he put the elements in like in a spring shape, and the spring has turns, and each turn starts here and ends here, and this is the beginning of the next turn of the spring. So you have here the elements arranged with the period, or with the atomic or the atomic mass, which is hydrogen, then lithium. You will notice that some elements are not there, and this is because at the time this was in April 1862, so they didn't explore all the elements. So there might be some elements that were missing or not explored at that time. And you see that it ends with oxygen, and here starts oxygen and then ends with sulfur, and then so on. So this is how he arranged the elements of the periodic table. He called it the tellurique screw, which is the cylindrical screw, which is like the spring, as I mentioned. So each turn increases by 16 units of atomic weight, and he used this 12, or the number of 16, because he noticed that the properties kind of repeat as he increases by 16. Then there was another attempt that was made in the late in 1800s by the German chemist Julius Lother Meyer, and he made a table that contained 28 elements. As you see, it was just a table with the elements, and it was based on the valency. So I put the elements with the valency of 4, then the valency of 3, then 2, then 1, then 1, then 2. And he put 20, or tabulated 28 elements here. And he and this was not very difficult actually to do, but the good thing that he did was he plotted the atomic volumes of the elements against the atomic weight, and this was very interesting. And you can see here that he just put carbon and then silicon and then This is the difference. Whatever you have nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, which is not is not difficult to put. You know the valency of each one of them, and you'll just put all of them together. And you'd see the famous halogens. It's fluorine, chlorine, bromine, which this should be iodine, and the alkali metals: lithium, sodium, potassium, rubidium. So this sounds like logical. Magnesium, calcium, beryllium, magnesium, calcium. So this is also logical. But the point here is this plot, and this is the atomic volume against the atomic weight. And this is against the atomic number. Actually, it's not the atomic weight. And you'd see that he found that there is a peak here in the atomic volume, and then it gets smaller, increases, small increase, and then decreases, and so on till you reach the potassium, and then you have a big increase. And you notice that this huge increase in the atomic volume is in the alkali metals. And for the other elements, they're all smaller than that. So he noticed that there is some sort of periodicity here, and he assumed that this is the at that time they didn't know, the board hadn't made his atomic model, so they were not very familiar with the periods and the atomic energy levels. So he didn't know that this is period 2, period 3, and period 4, but he noticed that there is repetition of the increase in the, or of the pattern in general. You have a small increase and then decrease, increase and then decrease. And he noticed that cesium, rubidium, potassium, where as we say here, they are all in one column. So this is how he noticed the periodicity of elements according to the atomic volumes. Then in 1869, Mendeleev discovered the periodic table, or he developed his periodic table. And as we said, he put the elements in the order of increasing of atomic weights first. And he found that there is some regular repetition of properties of elements. So, for example, he noticed that a reactive nonmetal, he was followed by a very reactive light metal, and then a less reactive light metal. So this was kind of pattern that he noticed. He also noticed that there are some elements that do not seem to be in the right place. So he was able to, or he decided to change the position of some elements because he didn't find that they are following the pattern that he found for the rest of elements. For instance, iodine and tellurium, he flipped them the other way, although the molecular weights were not in the right place. The interesting thing about this periodic table is that he was able to predict the presence of elements that were not explored yet. So, for instance, the element gallium was not explored when he developed his periodic table, and he was able to predict some properties of the elements, and he was very, very close to the actual results that were known later after exploring the element gallium. So he said the atomic weight will be around 68, and it's actually 69.72. The density is 6, and it's actually 5.9. He expected low melting point, and the melting point was 29.78. The valency is 3. The oxide is gallium oxide, Ga2O3, and it is Ga2O3, and the density is 5.88, and he expected to be 5.5. He called it EKA aluminum, which is like similar to aluminum because it's the next element, or the element directly beneath aluminum in the periodic table. And this is a very, very interesting thing. Then we will go back to Moseley, and we said that he plotted the frequency of the elements against the atomic number and the atomic weight, and found that the atomic number gives very, very linear relation, which is more accurate than the molecular weights. And then Mendeleev, or the periodic table, was then sorted according to the atomic number, not the atomic weight. So these are the attempts that were made to develop the periodic table. And finally, Mendeleev's periodic table is the one that seemed to be very, very accurate, and it answers many questions. In the next video, you'll see how why the periodic table looks like this, why the shape of the periodic table is not just a table. It has some lines that are, or rows that are bigger than the other rows. This is something that we will talk about next video, inshallah. I'll see you there.